My name is Christina Martinez. This is presentation 1 on the Leucine Zipper. The Leucine Zipper is depicted in this image on slide 1. All right, so moving forward, principles involved in holding the two alpha helixes together is the coiled-coil interaction between the hydrophobic repeat of the leucine residue. As depicted in this image, I went ahead and I circled the middle, the core here. The circles here are showing this is the hydrophobic portions that are going to be holding this core together. Keep in mind there is an aqueous medium out here. That will need to be notated so that the discussion further you understand. Now, one possible residue that can replace leucine is isoleucine. Isoleucine can maintain the hydrophobic core and the stability of the core because it is just as hydrophobic as leucine, has the same chain length as leucine, and the same molecular mass of 131. Also, the R groups of isoleucine and leucine are isomers of each other. Now, moving forward, a residue that can destabilize the core would be one that is hydrophilic. This is due to the fact that the medium surrounding is aqueous and the hydrophilic portion of the amino acid is not going to want to be pushed in the center, holding the helixes together. So if we go back to this image as depicted here, let's say instead of these being hydrophobic, this is hydrophilic. As I stated before, this is a aqueous solution here. So instead of the helix pushing in together, because hydrophobic does not want to be near the aqueous solution, right? So that's why they're pushing each other together. If this was hydrophilic, meaning it prefers the water, it's going to break apart and go more toward the aqueous solution. So we're not going to have that strong hold in the center, right? So the hydrophilic portion of the amino acid is not going to want to be pushed in the center, holding the helixes together. The hydrophilic portion is going to pull toward the aqueous medium and thus disrupting the core. The residue that is hydrophilic, as we see here, could be serine, threonine, cysteine, asparagine, and glutamine. Okay, now for prompt 2, it is asking for a different amino acid pair whose side chains can interact in a similar manner to glutamate and lysine. So let's go ahead and within our modules, there was a video that I watched and I wrote out this, the 20 amino acids, and I wrote out some information around them. So if we look here, glutamic acid is a negatively charged amino acid. And let's just move the camera up here. And lysine is a positively charged amino acid. So when we think of a different amino acid pair whose side chains can interact in a similar manner to glutamate and lysine, it would be a pair that resembles either of those charges. Lysine is a positively charged amino acid and glutamate is a negatively charged amino acid. So within those groups, within the negatively charged group, there is aspartic acid, right? So that would be our other alternative. Instead of glutamate, we would use aspartic. And instead of lysine, we have the option of either histidine or arginine. So the alternative pairs would be either aspartic acid with arginine or aspartic acid with histidine. And if we go back to the image here, that's where you have that potential electrostatic interaction due to the fact that there is a negatively charged amino acid and a positively charged amino acid. Keep in mind that the negatively charged does have an extra carboxylic acid, and the positively charged, the nitrogen there picks up an extra protein, which adds that positive charge to it. And that is the end of my presentation. I hope you enjoyed and have a better understanding now of the leucine zipper.